Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 35, Gases Part 1. We are now in Chapter 5 of your textbook. Here are our objectives for today's video. Pause here. So as you probably determined from the title of this video, Gases Part 1, we're going to be talking about gases for this entire chapter. We're going to have a separate chapter on liquids and solids. For gases, one of the most fundamental ways that we can measure properties of them is by measuring the pressure. Pressure is just force over area, measured using either a barometer or a manometer. Everything that is a barometer is also a manometer. Barometer is specific to atmospheric pressure. It's not something we're really going to need to distinguish between in our class. I just wanted you to have seen the differences between the two at least once. Pause here. So for experimental and historical reasons, we may be measuring pressure using multiple different units. So all of the units that are listed here are all very, very commonly used. Atmospheres, ATM, that is 1 atmosphere is about the pressure, atmospheric pressure, which is equal to 760 millimeters of mercury, even though you're thinking that's a unit of length, and you would be correct. It has to do with the fact that if you have a barometer that has mercury in it, you literally measure the distance that the mercury travels up. So that's the reason for that. Or torr, they're really the same thing. We could use it more or less interchangeably. And then in physics, it is more common to use Pascal. So 1 ATM is 101.325 PA. You don't need to memorize these things. You just need to be comfortable converting between all of these units. Pause here. All right, I'll start to work through this. I could have converted this to ATM first. Some of you might do that. That's totally fine if you do. Because 535 has 3 sig figs, my final answer must also have 3 sig figs. So that's why I rounded that way. And then for the last one, if you wanted to just realize that they're the same thing, that would be completely fine. I'm still going to show the calculation in case you didn't see that. But torr and millimeters of mercury can be used more or less interchangeably. Pause here. So the ideal gas law relates really 4 quantities together for an ideal gas. For the time being, you could assume that everything I give you is an ideal gas, and we'll talk actually much later on in this chapter about something that isn't ideal. So P stands for pressure, V for volume, N for number of moles. R is always a constant. I highly recommend that you just put that into your calculator, 0.08206. Liters atmospheres per mole Kelvin. Those units are not going to affect how you actually do problems with the ideal gas law. It just makes the units work out. And T is temperature. When you are doing calculations with the ideal gas law, everything must have the correct unit associated with it. So what that means is every pressure must be an ATM. So if it's given to you in something else, convert it to ATM. Volume has to be in liters, N has to be in moles, and T must be in Kelvin. Pause here. So I'm going to work through this. So I like to do these problems just by listing what's there. So it says 5.00 moles. So that's my N. I see that temperature is 298 Kelvin, so T is equal to 298 Kelvin. And then it says that we have it at 900 millimeters of mercury. So that's my pressure. I'm going to go ahead and convert that to ATM before I do the rest of the problem. And then from there, I start with PV equals nRT, but I'm looking for V here, so I just divide both sides by P. And then from here, I just plug in my numbers. Since my N, my T, and my P are all 3 sig figs, I'm going to round my final answer to 3 sig figs. But if they had different numbers of sig figs, I would round to the lowest number of sig figs. Pause here. So you may be able to figure this out conceptually, but I find that doing this mathematically, at least for me, is a little bit easier. So I'm just going to take this and solve for P. So then it says if temperature is halved. So you could plug numbers in and you would see that if you have temperature, you have pressure. That would be one way to do it. The way I look at it is I see that pressure and temperature are directly related since T is in the numerator of the fraction. Therefore, the way that one changes is the way that the other changes. For the second one, volume is compressed to half of its normal value. So one way you could do this is by plugging in original numbers. We could just make them all 1. It'll just make life easier. Well, you could really pick any number. So originally, my pressure is equal to or actually directly related to 1. But then let's half volume. So what I end up seeing is pressure will double. Conceptually, if you take a chamber of gas and you push it together, it makes sense the pressure will increase. If you ever try to actually force a sample of gas into a smaller volume, it is very, very difficult to do so. Now I'm going to do something similar for the other one where volume is doubled. You could just recognize that pressure and volume are indirectly related, therefore doubling volume will have pressure. That's totally fine, but I like to show it mathematically because oftentimes that just makes more sense to students. But then conceptually, it makes sense that pressure will go down if I am expanding the volume. I don't think I actually said this earlier in the video, but it's just very useful to think of pressure as being caused by collisions of gas molecules with the sides of the container. I'll actually write that down because I think a lot of you would benefit from including that in your notes. That is all for tonight's video. Thank you so much for watching and have a great night.